I want to take a moment to review our idea of forces. Forces are one of the most important things that we study in physics. They are the agents of change. These are the things that are going to make objects that were in motion change their motion, and objects that are at rest change their state of motion also. Remember that forces always come in pairs, and that forces must be equal and opposite. So that says in order for there to be a force, we need to have two objects. Each object will experience an equal force, but they will be in opposite directions. Okay, it's very obvious when we look at force of gravity that we need to have two objects, especially since the formula involves mass 1 and mass 2. What you may not realize is that both objects experience the exact same magnitude of force. It just so happens that they are in opposite directions. So as they attract each other, the two forces of attraction are equal but in opposite directions. As we saw, the force depends on the distance between the objects. As that distance increases, the force decreases. It's an inverse squared relationship, so that means 2 times the distance will give you 1/4 of the force. 3 times the distance will give us 1/9 of the force. Okay? As mass increases, for either object, the force is going to increase. This will be a linear or a direct relationship. Gravity turns out to be one of the weakest of the forces, and when we look at the strength of gravity between these two objects, we see, once we remove all of our text, that the force is incredibly weak, micronewtons. Okay, so that is force of gravity. Force electric is very similar to the force of gravity. It also can be attractive, but it can also be repulsive. So if we focus only on charge 1 and charge 2, we see that since they are both positive charges, they will repel each other. Again, this force depends upon the distance between them, and distance is going to be an inverse squared relationship, just like it was with gravity. Instead of masses like we had with gravity, it is now the product of the two charges. So the more charge that our objects have, the greater the force they will create. And then the value for the constant for electricity is going to be 9e to the 9th. This is much stronger force than gravity, where the constant was 6.67 e to the negative 11th. So of the fundamental forces, the electromagnetic force, in this case the electrostatic force, is much stronger than the force of gravity. Okay, the next force we want to take a moment to look at and review is the force normal. Remember that force normal is a contact force. Just like with all other forces, we need to have two objects. In this case, the box is in contact with the ice. So we have a force normal pushing up on the box, but we also have the box applying a force normal down to the ice. Again, equal and opposite forces. Force normal, the term normal means perpendicular, so normal must always act at a right angle to the two surfaces. We also have, in this case, a force tension. We see the tension is pulling on the box, but the box will also be pulling back on the rope. At this end, we see the force probe pulling on the rope and the rope pulling back on the force probe. Again, equal and opposite forces. When a force is in a rope or string or chain, it is often called the force tension. In this example, we can also see a force of friction. There's not a lot of force friction between the rubber and the ice, But as this person pulls the rubber across the ice, there's going to be a force friction between the rubber and the ice. The friction on the puck or box will be backwards, but at the same time, the box will try to pull the ice forwards. This is our force of friction. Just like force normal, it's a contact force between surfaces. It is different from force normal because it is going to be parallel to the surfaces, where force normal was perpendicular. Remember, force friction depends upon how much force is pushing the two surfaces together, which we call our force normal. And also, it depends upon the type of surfaces. Remember that just because you have a force normal does not mean that you have a force of friction. So before we actually start pulling the box across the table, there is no frictional force present. Okay, our elastic force is our next force. This is a restoring force. This occurs whenever an object is being deformed from its original shape and trying to pull itself back to its original shape. Okay, the force elastic depends upon the nature of the object being distorted and also the amount of distortion. So in this case, we have a force from the string pulling the spring in one direction. The spring will pull back with an equal amount of force. We can see at the other end that the spring is pulling the eye hook out of the wall, or at least trying to, and the eye hook is pulling back on the spring. These forces in the distorted object are called force elastic. As I said, they depend on the nature of the object, which is our spring constant or elastic constant. And they also depend on how much the object is being distorted. Sometimes you will see a negative sign placed in front of the force elastic, in front of the K delta X. If you see that, all it reminds you is that the force is in the opposite direction as the distortion. So if we stretch it to the right, the force is going to be to the left. But remember, there's actually a force elastic occurring on both sides of the object. The spring is trying to pull the rope backwards. It's trying to pull the eye hook forwards. So better would be to have just be an absolute value and just think about the direction of force elastic for each of the different cases that you might encounter. Okay, I also want to remind you that when your surfaces are not horizontal, but instead are on an angle, that your force normal and your force friction remain perpendicular and parallel. So if we were looking at this wooden box on this incline, force normal would be inclined at the same angle as the incline itself to remain perpendicular to the surfaces. Friction likewise would be inclined, and the friction would be acting, in this case, down along the surfaces. So as this mass tries to pull the other mass up the incline, friction is going to be acting down the incline. Were this mass light enough, this one may slide down the incline, in which case the force of friction would be up the incline. But again, the friction is parallel to the surface. And again, if the friction on this block is up the incline, then the block is exerting a frictional force on the incline in the opposite direction. So the key thing to remember, no matter which force you're dealing with, is that forces are always going to come in pairs. They require two objects, and they are equal and opposite in direction.